Hello everyone. In this video, we will learn to define the terms theoretical yield, actual yield, and percent yield. To calculate the percent yield for a chemical reaction. In the previous video, we have solved a limiting reactant problem, which is if 20 grams of nitrogen is mixed with 76 grams of hydrogen, how many grams of ammonia can be made? And we got an answer of 24.27 grams of ammonia. In practice, when you conduct this reaction in the lab with 20 grams of nitrogen and 76 grams of hydrogen, we can only make around 12 grams of ammonia, which is about half or 50% of what we are supposed to get. The 24.27 grams of ammonia, which we calculated, is the maximum amount of ammonia that can be produced when we mix 20 grams of nitrogen with 76 grams of hydrogen. This is called as theoretical yield. That is, the amount of product based on stoichiometric calculations. When we perform this reaction in the lab, we seldom get 24.27 grams of ammonia. The mass of ammonia we get is always less than 24.27 grams. Now, there could be several reasons why we don't get the maximum amount of ammonia. There could be some side reactions that happen in parallel to the desired reaction. The side reactions reduces the amount of desired product formed, or the reaction itself could be quite inefficient, or there could be some other technical complications involved. All these factors decreases the maximum amount of ammonia that can be made. The 12 grams of ammonia, that is the amount of ammonia we get in the lab, is called as actual yield. The actual yield is often expressed as a percentage of theoretical yield. That is, percentage yield is equal to actual yield divided by theoretical yield times 100. Since the actual yield is always less than the theoretical yield, the percent yield of any reaction is less than or very close to 100. If we calculate the exact percent yield for the above reaction, we get percent yield is equal to the actual yield, which is the amount that we got in the lab, that is 12 grams of ammonia, divided by theoretical yield, which is the amount of product that we calculated based on stoichiometry, which is 24.27 grams of ammonia times 100. Grams of ammonia gets cancelled. If we do the math, we end up getting 49.4%. So this is how we calculate the percentage yield of a particular reaction. Let us define the three types of yields again. The theoretical yield is the mass of product that is based on stoichiometric calculations. This is the maximum amount of product that can be produced from a reaction. The actual yield is the mass of product obtained when we actually perform the experiment in the lab. And the actual yield is always less than theoretical yield. The percentage yield is the ratio of actual yield to the theoretical yield times 100. Let us do an example problem. Oxygen gas reacts with nitrogen gas to form dinitrogen pentoxide. A balanced chemical equation for this reaction is given below. 2 moles of N2 reacts with 5 moles of O2 to form 2 moles of N2O5. The first question is, what is the maximum number of moles of dinitrogen pentoxide that can be made when you mix 2 moles of N2 with 10 moles of oxygen? The question is asking us to calculate the maximum amount of product that can be made. That means we need to calculate the theoretical yield, and which can be calculated based on stoichiometry. Now, this is a limiting reactant type problem because both the starting materials are given. Let us set up the reaction table or ICE table. We can also do this problem without the reaction table. At the beginning, we have 3 moles of nitrogen and 10 moles of oxygen, and we do not have any product formed yet. That is 0 moles of N2O5. As we discussed in the earlier video, to fill the change column, we need to first identify the limiting reactant. So, I will use one of the two methods that we discussed earlier. I will assume only the moles of nitrogen is given as 3 moles and determine how many moles of oxygen is required to completely consume 3 moles of nitrogen. According to the equation, 2 moles of nitrogen can react with 5 moles of oxygen. We can use this as a conversion factor. We start with 3 moles of nitrogen and multiply it with a conversion factor that has moles of nitrogen in the denominator and moles of oxygen in the numerator. And from the balanced equation, we can write 5 moles of oxygen per 2 moles of nitrogen. The moles of nitrogen gets cancelled, and if we do the math, we get 7.5 moles of oxygen. That is, to completely consume 3 moles of nitrogen, we need 7.5 moles of oxygen. In the reaction mixture, we have 10 moles of oxygen, which is higher than what is required to completely consume 3 moles of nitrogen. Therefore, the nitrogen gas is the limiting reactant and oxygen gas is the excess reactant. And we know that the limiting reactant, by definition, will be completely consumed in the reaction. Therefore, the change for N2 gas is minus 3 moles. Now, to fill the change for oxygen gas, I ask a question. If 3 moles of nitrogen is consumed, how many moles of oxygen will be consumed? We already calculated this earlier, which is 7.5 moles. Therefore, the change for oxygen is minus 7.5 moles. Next, let's calculate the change for N2O5. Now we ask a question. If 3 moles of N2 is consumed, how many moles of N2O5 is produced? According to the equation, which is balanced, 2 moles of N2 makes 2 moles of N2O5. We can again use this as conversion factor. We start with 3 moles of N2 and multiply it with a conversion factor that has moles of N2 in the denominator and moles of N2O5 in the numerator. And the ratio is 2:2. The moles of N2 gets cancelled. If we do the math, we get 3 moles of N2O5. So the change for N2O5 is plus 3 moles. So at the end, we have 0 moles of N2 left, which is expected for limiting reactant, 2.5 moles of oxygen left, which is an excess reactant, and 3 moles of N2O5 formed in the reaction. This is the maximum number of N2O5 that can be made when we mix 3 moles of N2 and 10 moles of oxygen. This also is known as theoretical yield. Question number 2. How many moles of dinitrogen pentoxide can be actually made if the reaction is only 25% efficient? The 25% efficiency represents the percent yield of the reaction, and we need to calculate the moles of N2O5 actually made, that is the actual yield of the reaction. We know that the percent yield is equal to the actual yield divided by theoretical yield times 100. And we already calculated the theoretical yield in the previous problem, which is 3 moles of N2O5. We plug in the percent yield and theoretical yield into the formula and determine the actual yield. Actual yield is equal to percent yield times theoretical yield divided by 100. That is 25 times 3 moles of N2O5 divided by 100. If we do the math, we get 0.75 moles of N2O5. Third question. What is the minimum number of moles of nitrogen we should start with to make 12.5 moles of N2O5? Assume the reaction is 25% efficient. We are given the percent yield of the reaction and that we need to make 12.5 moles of N2O5. This is the actual yield, and we need to calculate the moles of N2 required. We cannot use the actual moles of N2O5 to calculate the moles of N2 required. We need the theoretical moles or theoretical yield of N2O5 to do so. We can use the percent yield and actual yield to calculate first the theoretical yield of N2O5. The theoretical yield of N2O5 is equal to actual yield divided by percent yield times 100. If we plug in the numbers, we get 12.5 moles of N2O5, which is actual yield, divided by percent yield, which is 25 times 100. If we do the math, we end up getting 50 moles of N2O5. This is the theoretical yield of N2O5, and using which we can actually calculate the number of moles of N2 required. So the next question is, how many moles of N2 is required to make 50 moles of N2O5? According to the balanced equation, 2 moles of N2 produces 2 moles of N2O5. Therefore, to produce 50 moles of N2O5, we need 50 moles of N2 to begin with. So the minimum number of moles of N2 to start the reaction is 50. In this problem, the amounts of reactants and products are given in terms of moles. However, to make things a little bit more complicated, we can give the amounts of reactants and products in terms of grams. We use same steps to solve that problem. However, there will be an additional step of converting grams of reactants into moles or moles of reactants into grams, depending on the problem.